Imagine standing at the edge of everything you've ever known. The stars, the planets, the galaxies, all part of a vast universe that stretches billions of light years in every direction. But what if this is just the beginning? What lies beyond the universe? Is there an outside to everything, or does the question itself unravel the fabric of reality? This documentary explores one of humanity's most profound mysteries, drawing on centuries of scientific inquiry, philosophical debate, and cutting-edge theories. From ancient myths to modern cosmology, we'll journey into the unknown, questioning the very nature of existence. The universe, by definition, encompasses all space, time, matter, and energy. In cosmology, it's often described as everything that exists. Yet, human curiosity compels us to ask, if the universe has boundaries, what fills the void beyond? Or if it's infinite, how do we comprehend eternity? These questions have puzzled thinkers for millennia, and today, with tools like the James Webb Space Telescope peering deeper into space than ever before, we're closer to answers. Or perhaps just more intriguing questions. Our quest begins in antiquity. For early civilizations, the universe was the visible sky, a dome of stars encircling Earth. The ancient Greeks, like Aristotle, envisioned a finite cosmos with Earth at the center, surrounded by crystalline spheres carrying the planets and stars. In Eastern philosophies, such as those in the Vedas of ancient India, the universe was cyclical, infinite in time, with endless cycles of creation and destruction. Similarly, indigenous cultures worldwide spoke of other realms or spirit worlds existing parallel to our own, accessible through dreams or rituals. The Renaissance shifted perspectives. Nicholas Copernicus displaced Earth from the center, and Giordano Bruno boldly proposed an infinite universe filled with countless worlds, a heretical idea that cost him his life in 1600. Bruno's vision foreshadowed modern multiverse theories, imagining stars as distant suns with their own planets, extending endlessly. As telescopes improved, so did our understanding. Edwin Hubble's 1920s discoveries revealed the universe is expanding, leading to the Big Bang Theory, a singular event 13.8 billion years ago from which all space-time emerged. But if the universe began with a bang, what preceded it? And if it's expanding, into what? Today we distinguish between the observable universe and the entire universe. The observable part is a sphere about 93 billion light-years across, limited by the speed of light and the universe's age. Light from farther away hasn't reached us yet. Beyond this horizon, more of the same. Galaxies, stars, perhaps even identical copies of our solar system due to quantum probabilities in an infinite space. But is the universe finite or infinite? General relativity allows for both. A finite universe might be curved like a sphere's surface, unbounded but limited with no edge. An infinite universe, however, stretches forever, with no beyond because there's no end. The Big Bang wasn't an explosion in space, it was the expansion of space itself. There's no outside in the traditional sense, space is creating more space as it expands, yet this doesn't satisfy our intuition. If the universe is everything, how can there be something else? Enter the multiverse, the idea that our universe is one of many. This isn't science fiction, it's rooted in physics. First, inflationary multiverse theory. Cosmic inflation, a rapid expansion right after the Big Bang, suggests eternal inflation, where pockets of space stop inflating and form bubble universes. Ours is one bubble in a vast inflating sea. Evidence? The uniformity of the cosmic microwave background radiation supports inflation, though direct proof of other universes remains elusive. Critics argue this is untestable speculation. If other universes are causally disconnected, how can we observe them? Some point to CMB anomalies like the cold spot as potential collisions with neighboring universes, but this is debated. Quantum mechanics offers the many worlds interpretation. Every quantum decision branches into parallel universes. Schrödinger's cat is both alive and dead in different worlds. No direct evidence, but it resolves quantum paradoxes without collapse. Detractors call it philosophical, not empirical. String theory posits extra dimensions up to 11, where our universe is a brain floating in higher dimensional space. Other brains could be parallel universes. Criticisms include lack of falsifiability and no experimental confirmation. Black hole cosmology speculates our universe is inside a black hole in a larger cosmos, with event horizons as boundaries. Philosophy probes deeper. Immanuel Kant argued space and time are human intuitions, not objective realities. Perhaps the beyond is unknowable. Panpsychism suggests consciousness pervades the universe, implying a moral or purposeful outside. Religious views vary. In Abrahamic traditions, God exists beyond creation. Hinduism's Advaita Vedanta sees the universe as illusion, with true reality in Brahman. Simulation theory proposes we're in a computer program, with the beyond being the simulator's reality. Evidence, quantum weirdness and fine-tuned constants, but it's unfalsifiable. On X, users speculate wildly, from orbs as ancient civilizations to alien invasions. One post questions if we're inside a black hole, echoing fringe theories. Evidence for multiverses is indirect. Fine-tuning of constants, why are they perfect for life, suggests selection from many universes. But anthropic principle counters, we observe what allows us to exist. Criticisms abound. Multiverses are pseudoscience, lacking testability. Future probes like gravitational wave detectors might detect multiverse signatures. Recent discussions highlight interstellar objects like 3I/Atlas as potential alien probes, though likely natural. What lies beyond the universe? Science offers multiverses, infinities and cycles. Philosophy, realms of mind and spirit. Perhaps it's nothingness, an infinite void. Or maybe the question reveals our limits. As we peer deeper, remember, the universe isn't just out there, it's within us, in our quest to understand. The beyond may forever elude us, but the journey enriches our existence. In the vast expanse of our solar system, beyond the icy realms of Neptune and Pluto, lies a mystery that has captivated astronomers, scientists, and stargazers alike for over a century. Does a ninth planet truly exist? This documentary delves into the heart of this enduring question, exploring the tantalizing clues, the heated debates, and the cutting-edge searches that continue to unfold as of August 2025. From early speculations in the 19th century to the revolutionary hypothesis proposed in 2016, we'll journey through the evidence suggesting a massive, unseen world lurking in the darkness, while confronting the skeptics who argue it's all an illusion of data and bias. As telescopes grow more powerful and supercomputers simulate cosmic dances, the search for Planet 9 isn't just about finding a planet, it's about rewriting our understanding of how solar systems form and evolve. The story begins in the early 1900s, when astronomers like Percival Lowell hypothesized a Planet X to explain irregularities in the orbits of Uranus and Neptune. Lowell's quest, driven by mathematical predictions, led to the discovery of Pluto in 1930, but Pluto proved too small to account for those perturbations, which were later attributed to measurement errors. For decades, the idea of an undiscovered planet faded into obscurity, dismissed as a relic of outdated astronomy. Yet the outer solar system held secrets. In 2003, the discovery of Sedna, a distant reddish world with an elongated orbit, reignited curiosity. Sedna's path, stretching far beyond Neptune, hinted at gravitational influences from something massive and unseen. Astronomers began cataloging more trans-Neptunian objects, extreme worlds with orbits that defied simple explanations. Fast forward to January 2016, when Caltech astronomers Konstantin Batygin and Mike Brown unveiled their groundbreaking paper proposing Planet 9 as the culprit behind these orbital oddities. Analyzing 6 extreme TNOs, they found their orbits aligned in a peculiar way, their closest approaches to the Sun bunched together, and their paths tilted similarly relative to the solar system's plane. Simulations showed that a planet roughly 5 to 10 times Earth's mass, orbiting at 400 to 800 astronomical units from the Sun, 1 AU being the Earth-Sun distance, could shepherd these objects into such configurations. This wasn't mere speculation. The probability of such clustering occurring by chance was a minuscule 0.007%. Batygin and Brown argued that Planet 9's influence would create anti-aligned orbits, where TNOs avoid close encounters with the hypothetical giant, much like sheep herded by an invisible shepherd. Their work built on earlier observations by Chad Trujillo and Scott Shepard, who in 2014 noted similar alignments in objects like Sedna and 2012 VP 113. As evidence mounted, so did the details of what Planet 9 might look like. Early models painted it as a gaseous super-Earth or mini-Neptune, with a thick hydrogen-helium atmosphere enveloping a rocky core, perhaps ejected from the inner solar system during its chaotic formation billions of years ago. By 2025, refined simulations by Amir Siraj and colleagues pegged its mass at about 4.4 Earth masses, with a semi-major axis of around 290 AU, an eccentricity of 0.29, and a slight inclination of 6.8 degrees. Its orbital period could span 5,000 years, making it a dim, cold wanderer, reflecting faint sunlight at temperatures plummeting to -200 degrees Celsius. Proponents point to additional anomalies, the solar system's 6-degree tilt relative to the sun's equator, which Planet 9's gravity could explain, and the existence of high-inclination TNOs flipped nearly perpendicular to the ecliptic plane. Yet, for every piece of supporting data, skeptics offer counterpoints, arguing that Planet 9 might be a ghost in the data. One major criticism stems from observational bias. Telescopes like Pan-STARRS and the Dark Energy Survey scan the sky unevenly, favoring certain regions and potentially creating artificial clusters. The Outer Solar System Origins Survey in 2019 analyzed 836 TNOs and found no significant clustering after accounting for these biases, suggesting the alignments could be coincidental. Alternative explanations abound. Perhaps a massive disk of icy bodies totaling 20 Earth masses could collectively gravitationally shepherd the TNOs through inclination instability, a process unfolding over billions of years. Or, the anomalies might arise from Neptune's ancient migration, scattering objects in ways that mimic a planet's influence. Some even propose Planet 9 as a primordial black hole, a stellar remnant the size of a grapefruit but with Earth's mass, detectable via Hawking radiation or microlensing, though no such signals have emerged. Searches for Planet 9 have been exhaustive, yet fruitless so far, fueling doubts about its reality. NASA's Wide Field Infrared Survey Explorer and NEOWISE missions scoured the skies for thermal emissions from a cold, distant world, ruling out gas giants larger than Saturn beyond 10,000 AU but leaving room for smaller bodies. The Zwicky Transient Facility eliminated 56% of predicted parameter space by 2021, while the Transiting Exoplanet Survey satellite scanned for moving points of light without success. Ground-based efforts, like those with the Subaru telescope in Hawaii, have imaged vast swaths of sky identifying new TNOs but no Planet 9. Citizen science projects such as the Catalina Outer Solar System Survey enlisted public help to sift through data, wrapping up in May 2025 with valuable contributions but no breakthrough. Even the Cassini spacecraft's precise measurements of Saturn's orbit constrained possible locations, suggesting if it exists, Planet 9 must be farther out or less massive than initially thought. The year 2025 has brought a flurry of new developments injecting fresh optimism and controversy into the debate. In May, astronomers announced the best candidate yet for Planet 9's influence. A July discovery of a new tiny world beyond Neptune dubbed a wide-orbit planet bolstered the theory, as its path aligns with predictions from Planet 9 simulations. Researchers at Rice University proposed that such wide-orbit planets form like pinballs in a cosmic arcade, scattered by gas giants and stabilized by a distant Planet 9 around high metallicity stars. Social media and public discourse in 2025 reflect this excitement, with X buzzing about potential breakthroughs. Users share supercomputer simulations and speculate on visibility. However, misinformation abounds, like an April Fool's joke claiming James Webb Space Telescope images of planet G34, which fooled thousands before being debunked. Looking ahead, the Vera C. Rubin Observatory, set to become fully operational soon, promises to revolutionize the hunt. Its wide-field surveys could detect faint objects at extreme distances, potentially spotting Planet 9 within years if it exists. Gravitational wave detectors or future missions might probe for its subtle tugs. In conclusion, as of August 2025, Planet 9 remains a compelling hypothesis, neither proven nor disproven. This cosmic detective story underscores humanity's drive to explore the unknown, reminding us that in the solar system's shadowy fringes, wonders, or illusions, await. The origin of life, from cosmic whispers to Earth's first spark. In the grand tapestry of existence, few questions loom as profoundly as the origin of life. How did inanimate matter transform into the teeming biosphere we inhabit today? This documentary explores the enigma of abiogenesis, the natural emergence of life from non-living substances, tracing its roots through billions of years of Earth's history and beyond. As of August 2025, scientific inquiry has unveiled tantalizing clues, from ancient hydrothermal vents bubbling with chemical potential to meteorites carrying the building blocks of biology across the stars. Yet the puzzle remains incomplete, blending chemistry, physics, geology, and astrobiology into a narrative that challenges our understanding of what it means to be alive. We'll journey from historical speculations to cutting-edge experiments, examining theories like the primordial soup, RNA world, and panspermia, while confronting recent discoveries that both illuminate and complicate the story. The quest to unravel life's beginnings dates back millennia, intertwined with philosophy and early science. Ancient thinkers like Aristotle proposed spontaneous generation, suggesting that simple organisms arose directly from decaying matter, a view that persisted until the 19th century when experiments by Louis Pasteur definitively disproved it, showing that life comes only from pre-existing life under modern conditions. This shifted focus to abiogenesis, the idea that life emerged from chemical processes on a primordial Earth. Charles Darwin, in an 1871 letter, mused about a warm little pond, rich in ammonia and phosphoric salts, where light, heat and electricity might spark the first proteins. This evolved into the Oparin-Haldane hypothesis in the 1920s, positing a primordial soup of organic compounds in Earth's early oceans, formed under a reducing atmosphere of methane, ammonia and hydrogen. The planet, formed about 4.54 billion years ago during the Hadean Eon, was a hellish world of molten rock, volcanic eruptions and comet bombardments. Yet by 4.1 billion years ago, evidence from ancient zircons hints at liquid water and possibly biogenic carbon, suggesting life arose remarkably quickly after the surface cooled. Pivotal to modern understanding was the 1952 Miller-Urey experiment, where Stanley Miller and Harold Urey simulated early Earth conditions in a flask, zapping a mixture of gases with electrical sparks to mimic lightning. The result? Amino acids, the building blocks of proteins, emerged spontaneously, proving that organic molecules could form abiotically. Later refinements accounted for a less reducing atmosphere, incorporating neutral gases like carbon dioxide and nitrogen, and still yielded diverse amino acids when bolstered by minerals like iron and carbonates. This experiment inspired decades of research, including syntheses of nucleobases from hydrogen cyanide and formamide, which can produce ribonucleotides under high-energy conditions. A 2024 study even used sapphire substrates to mimic deep ocean vents, concentrating prebiotic molecules to form biopolymers like peptides, highlighting how mineral surfaces could catalyze life's assembly. These lab recreations underscore that the raw ingredients for life, amino acids, sugars, lipids, and nucleobases, could plausibly arise from simple chemistry, driven by energy sources like UV radiation, geothermal heat, or cosmic rays. Among the leading theories, the RNA world hypothesis stands out, proposing that RNA molecules were the first self-replicating entities, serving dual roles as genetic material and catalysts, ribozymes. Unlike DNA, which requires proteins for replication, RNA can fold into shapes that speed up reactions, as seen in modern ribosomes. This resolves the chicken and egg paradox. Which came first, proteins or nucleic acids? Evidence includes ribozymes that catalyze peptide bonds and experiments showing RNA replication in prebiotic conditions. A 2025 life study demonstrated how gas flow over water in narrow channels could drive isothermal DNA replication, suggesting low-temperature settings for early molecular evolution. Complementing this is the metabolism-first approach, which argues that life began with energy-harnessing chemical networks, such as those at hydrothermal vents. The iron-sulfur world theory, for instance, envisions metal sulfide compartments where redox reactions, electron transfers between iron and sulfur, powered the synthesis of organic compounds, mirroring modern microbial metabolism. Hydrothermal vents, discovered in the 1970s, emerge as prime candidates for life's cradle. These deep-sea fissures spew superheated mineral-rich water, creating gradients of temperature, pH, and chemistry ideal for prebiotic reactions. Black smokers, with their iron sulfide chimneys, could trap and concentrate molecules, while alkaline vents offer proton gradients akin to those in cell membranes, potentially fueling the first protocells. A 2025 Harvard experiment with synthetic self-assembling materials simulated how such environments might birth primitive life forms, showing spontaneous organization into cell-like structures. On land, hot springs and geothermal pools provide wet-dry cycles that dehydrate and concentrate organics, facilitating polymerization. Recent research challenges older assumptions. A May 2025 study debunked the foremost reaction's role in sugar formation under prebiotic conditions, as it fails to produce stable linear ribose, prompting re-evaluation of how RNA precursors arose. Another twist came in June 2025, suggesting amino acids formed in a specific order, with simpler ones preceding complex structures, reshaping timelines of biochemical evolution. Panspermia adds a cosmic dimension, theorizing that life or its precursors originated elsewhere and hitched a ride to Earth via meteorites, comets, or interstellar dust. Ancient Greek philosopher Anaxagoras first floated the idea, but modern evidence bolsters it. Carbonaceous chondrites like the Murchison meteorite contain amino acids, nucleobases, and sugars, some with chiral biases mirroring life's handedness. A July 2025 discovery of all DNA and RNA bases in meteorites strengthened this, implying space-seeded organics during the late heavy bombardment around 3.9 billion years ago. Rowan University's 2025 research, overseen by Professor Connolly, analyzed meteoritic samples, confirming complex organics could survive atmospheric entry and seed prebiotic chemistry. This aligns with astrobiology's hunt for life on Mars or Europa, where subsurface oceans might harbor similar vents. NASA's astrobiology program emphasizes these extraterrestrial contributions, with missions like Perseverance rover sampling Martian rocks for biosignatures. Delving deeper, the last universal common ancestor, Luca, offers a genomic window into early life. Estimated at over 4 billion years old, Luca was likely a thermophilic anaerobe with DNA, ribosomes, and metabolic pathways like the wood Ljungdahl for carbon fixation. A 2025 study challenged assumptions about ancient proteins, revealing they were more flexible than thought, aiding adaptation in harsh environments. Fossil records support an early start. 3.5 billion-year-old stromatolites in Australia and potential 4.1 billion-year-old microfossils indicate prokaryotes thrived soon after Earth's habitability. Yet, homochirality, life's preference for left-handed amino acids and right-handed sugars, remains mysterious, possibly arising from asymmetric autocatalysis or cosmic influences like polarized starlight. Recent breakthroughs in 2025 have electrified the field. A March experiment recreated micro-lightning in water droplets, showing how electric discharges could forge life's building blocks in ancient atmospheres. April's findings overturned theories on Earth's water origin, suggesting it formed naturally rather than via asteroid delivery, impacting prebiotic models. In August, a New Scientist article detailed a microbial partnership between bacteria and archaea, hinting at how eukaryotes evolved 2 billion years ago through symbiosis. Michael Levin's February paper framed origins as a cognitive problem, arguing all persistent systems exhibit minimal cognition under the free energy principle, blurring lines between life and non-life. A PNAS study proposed protocells formed under a plausible early atmosphere, combining chemistry and compartmentalization. Critics, including chemist James Tour in July 2025, argue that key steps like RNA self-assembly remain improbable, undermining pillars of origin theories. Creationist perspectives from the Institute for Creation Research claim irreproducible complexity points to design, but mainstream science counters with evolutionary gradualism. A bold February theory posits hard steps in evolution, where permissive environments enable complex life, upping odds for extraterrestrial intelligence. Applying Moore's law to genetic complexity even suggests life predates Earth by billions of years, fueling panspermia debates. As we peer into 2025's horizon, initiatives like Harvard's Origins of Life program and the Danish Symposium convene experts to bridge gaps. Future missions to icy moons and exoplanets promise biosignatures, while lab simulations refine models. The origin of life isn't just Earth's story. It's a universal saga, whispering that in the cosmos's vastness, we may not be alone. From primordial sparks to sentient beings, this journey reminds us, life, resilient and ingenious, finds a way. Beneath the ice, the quest for life on Jupiter's moons. Jupiter, the colossal gas giant of our solar system, reigns as a planetary behemoth. But it's the enigmatic worlds orbiting it that have ignited humanity's imagination about extraterrestrial life. Discovered by Galileo Galilei in 1610, the 4 largest moons, Io, Europa, Ganymede, and Callisto, form a miniature solar system teeming with geological wonders. While Io erupts with volcanic fury, the icy trio of Europa, Ganymede, and Callisto harbors secrets beneath their frozen exteriors, vast subsurface oceans that could potentially cradle life. As of August 2025, no definitive evidence of life has been found on any of Jupiter's moons, Yet the tantalizing clues from decades of observations and ongoing missions paint a picture of habitability that rivals Earth's ancient seas. This documentary delves into the scientific odyssey, from historical glimpses to cutting-edge explorations, examining whether these distant worlds might host microbial ecosystems or even more complex forms, reshaping our understanding of life's tenacity in the cosmos. The story begins with Galileo, whose rudimentary telescope revealed these moons as dynamic bodies, challenging the geocentric view of the universe. Fast forward to the space age, NASA's Pioneer and Voyager missions in the 1970s provided the first close-ups, unveiling Europa's smooth, cracked ice shell, Ganymede's grooved terrain, and Callisto's cratered antiquity. The Galileo spacecraft, orbiting Jupiter from 1995 to 2003, revolutionized our knowledge by detecting magnetic anomalies suggesting salty oceans beneath the ice on all three moons. Europa emerged as the star. Its induced magnetic field, triggered by Jupiter's powerful magnetism, indicated a conductive layer, likely a global ocean of liquid water, possibly twice the volume of Earth's seas. Hubble Space Telescope observations in 2012 spotted potential water vapor plumes erupting from Europa's surface, hinting at geysers that could eject ocean material into space, offering a window into its hidden depths. Ganymede, the largest moon in the solar system, bigger than Mercury, boasts its own magnetic field, a rarity among moons generated by a molten iron core. Data from Galileo and subsequent analyses suggest a layered ocean sandwiched between ice sheets, potentially 100 kilometers deep but isolated from the rocky seafloor by high-pressure ice, which might limit nutrient cycling essential for life. Callisto, the most distant and heavily cratered, appears less geologically active. Yet recent 2025 studies propose a subsurface ocean enriched with salts and organics, possibly sustained by radiolytic processes where cosmic radiation breaks down ice into hydrogen and oxygen, fueling potential microbial habitats. Unlike Europa's dynamic environment, Callisto's ocean might be a quiet, ancient reservoir, but its stability could allow for long-term biological evolution. Io, by contrast, is a hellish world of sulfurous volcanoes and lava lakes, driven by tidal heating from Jupiter's gravity. Its extreme conditions make life improbable, though it influences the Jovian system by spewing particles that interact with the other moons' atmospheres. The potential for life hinges on three key ingredients: liquid water, energy sources, and organic chemistry. Europa excels here. Its ocean likely contacts a rocky mantle, where hydrothermal vents, similar to Earth's black smokers, could release heat and minerals, fostering chemosynthetic life forms that thrive without sunlight. Tidal flexing from Jupiter's gravity generates internal heat, preventing total freeze-over and possibly powering cryovolcanoes that eject water plumes. Organic molecules detected in Europa's surface ices via spectroscopy might originate from cometary impacts or internal processes. Astrobiologists theorize that if life exists, it could mirror Earth's extremophiles, like those in Antarctic lakes or deep-sea vents. Recent models suggest radiation from Jupiter's belts could penetrate the ice, creating oxidants that mix into the oceans, potentially supporting redox-based metabolisms. Missions are the linchpin in this quest. NASA's Europa Clipper, launched in October 2024, is en route to Jupiter, set to arrive in 2030 for dozens of flybys. Equipped with ice-penetrating radar, spectrometers, and magnetometers, it will map the ocean's depth, salinity, and composition, hunting for biosignatures in plumes without landing. As of August 2025, the spacecraft has successfully tested its instruments, including a new radar designed to detect subsurface features, passing crucial in-space validations. The ESA's JUICE mission, launched in April 2023, complements this by focusing on Ganymede, with orbital insertion in 2034, alongside flybys of Europa and Callisto starting in 2032. NASA's Juno, extended through September 2025, continues to gather data on Jupiter's environment, indirectly aiding moon studies with flybys of Europa and Io. In 2025, excitement builds with fresh insights. An August article highlights that discovering life on Europa would be humanity's most profound space breakthrough, underscoring the moon's oceans as analogues to Earth's primordial conditions. April's research on cryovolcanoes suggests active geology on Europa, potentially exposing ocean materials. Social media buzzes with speculation. X-users discuss NASA's radar tests and cosmic radiation as energy sources for life, while others ponder if these worlds teem with biology. Challenges abound. The The moon's harsh radiation belts, thin atmospheres, and extreme cold pose barriers to life and exploration alike. Detecting life requires sampling plumes or drilling through ice, feats beyond current tech, though future landers are conceptualized. Ethical questions arise. If microbes exist, how do we avoid contamination? Planetary protection protocols guide missions, but a 2025 discussion in Provincetown Independent ponders what we'd defend if life is found: our scientific curiosity or pristine alien ecosystems. As missions hurtle toward Jupiter, the question lingers: are we alone? Jupiter's moons offer a cosmic laboratory where icy worlds might harbor life's whispers. No life has been confirmed as of August 2025, but the evidence mounts: subsurface oceans, energy gradients, organics, suggesting habitability. Discoveries here could imply life is commonplace, born in water worlds across the galaxy. In this frozen frontier, the search continues, bridging science and wonder, reminding us that life's spark may flicker far beyond Earth's shores. Voyager's Odyssey, echoes from the interstellar void. Launched in the summer of 1977 amid the backdrop of a rapidly advancing space age, NASA's Voyager 1 and Voyager 2 spacecraft embarked on what was initially a grand tour of the outer planets: Jupiter, Saturn, Uranus, and Neptune. Designed to last just 5 years, these twin probes defied expectations, venturing farther than any human-made object before them. Voyager 1, taking a faster trajectory after its Saturn flyby, became the first to pierce the heliosphere, the sun's protective bubble of solar wind and magnetic fields, in August 2012, entering the vast expanse of interstellar space. Voyager 2 followed suit in November 2018, providing a comparative dataset from a different path. Now, as of August 2025, both probes continue to transmit faint signals from billions of miles away, revealing the harsh, enigmatic environment beyond our solar system. Their instruments, though aging and power-constrained, have detected phenomena that challenge our understanding of cosmic boundaries, from plasma waves humming through the void to surges in galactic cosmic rays, painting a picture of a dynamic interstellar medium teeming with invisible forces. The heliopause, the boundary where the solar wind gives way to interstellar plasma, marked a pivotal milestone for the Voyagers. As Voyager 1 approached this frontier around 2012, its instruments recorded a dramatic shift. The intensity of low-energy charged particles from the sun plummeted, while high-energy cosmic rays from distant supernovae and galactic sources spiked threefold. This transition wasn't abrupt but unfolded over months, with the probe encountering regions of fluctuating magnetic fields and particle densities. Scientists interpreted this as the spacecraft crossing into the interstellar medium, where the sun's influence wanes. Voyager 2's crossing in 2018 echoed these findings but added nuance. Its plasma science instrument, still operational unlike Voyager 1's which failed in 1980, directly measured a sharp drop in solar wind plasma density, confirming the boundary at about 119 astronomical units from the Sun, 1 AU being the Earth-Sun distance. Both probes detected a wall of hot plasma at the heliopause, with temperatures soaring to 50,000 Kelvin, far hotter than predicted, suggesting compressive heating as solar wind collides with interstellar gas. This fiery barrier, while not impenetrable, Voyagers pass through unscathed, highlights the turbulent interface between our stellar neighborhood and the galaxy at large. Beyond the heliopause, the Voyagers unveiled the interstellar magnetic field, a subtle yet pervasive force shaping the cosmos. Voyager 1's magnetometer detected that the magnetic field in interstellar space is stronger and more compressed than anticipated, draped around the heliosphere like a cosmic blanket, with strengths around 0.5 nanotesla, about twice that inside the bubble. Surprisingly, the field's direction remained aligned with the heliospheric field, defying models that predicted an abrupt reorientation. Voyager 2 corroborated this, measuring similar field strengths but noting slight turbulence, possibly from shock waves rippling through the medium. These observations suggest the heliosphere compresses the interstellar field, creating a draped configuration that influences how cosmic rays infiltrate our system. The probes also sensed interstellar plasma, denser and cooler than the solar wind, with Voyager 2's direct measurements revealing electron densities about 0.03 particles per cubic centimeter, aligning with expectations from pulsar observations. One of the most intriguing detections came from Voyager 1's plasma wave instrument, a persistent, faint hum in the interstellar medium, first reported in 2021. This low-frequency oscillation around 3 kHz resembles the gentle drone of ocean waves, arising from vibrations in the interstellar plasma triggered by solar flares or electron beams. Unlike the sporadic plasma waves inside the heliosphere, this hum is nearly constant, offering a soundtrack to the void and insights into the density and temperature of the surrounding gas. Voyager 2 has detected similar waves, though its data is sparser due to power constraints. Galactic cosmic rays, high-energy particles from supernovae, black holes, and other galactic phenomena dominate the interstellar detections. Upon crossing the heliopause, both Voyagers recorded a surge in these rays, with intensities rising by factors of 100 for some energies, as the Sun's magnetic shield no longer deflects them. Voyager 1's cosmic ray subsystem has charted anomalies, such as temporary dips in ray intensity correlated with solar activity, indicating that even in interstellar space, the Sun's influence lingers through magnetic connections. Recent years have brought operational drama to the Voyager's interstellar saga. In November 2023, Voyager 1 suffered a glitch in its flight data subsystem, garbling science transmissions into unintelligible binary code. By April 2024, engineers at NASA's Jet Propulsion Laboratory devised a workaround, restoring coherent data by May, allowing the probe to resume sending plasma wave and magnetic field readings. As of August 2025, Voyager 1 is fully operational again, with all 4 remaining instruments active following a December 2024 power supply fix that averted a communications blackout. Voyager 2, trailing at about 13 billion miles, faces similar power woes. In March 2025, NASA shut down 2 instruments to extend its lifespan, yet it continues detecting interstellar plasma and fields. These efforts underscore the probe's resilience, with projections suggesting they could transmit until 2030 or beyond, albeit with fewer instruments. Sensational reports in 2025 have highlighted mysterious findings, such as Voyager 1's alleged detection of a 90,000 degrees Fahrenheit plasma wall or impossible structures. But these stem from misinterpretations of the heliopause data. More grounded discoveries include refined maps of the heliosphere's shape, an asymmetric bubble distorted by interstellar winds, and evidence of electron foreshocks, precursors to bow shocks around stars. Voyager 1 is poised for a historic milestone. By November 2026, it will reach 1 light day from Earth, about 16 billion miles, symbolizing humanity's farthest reach. Meanwhile, both probes carry the golden record, a message to potential extraterrestrials, though their primary legacy is scientific, illuminating the transition from solar to galactic dominance. The implications of Voyager's detections ripple across astrophysics and astrobiology. By sampling pristine interstellar material, they've confirmed the local interstellar cloud, a fluffy region of gas and dust our system traverses, has a temperature around 7,000 Kelvin and low density, influencing planetary climates and cosmic ray exposure on Earth. These findings challenge earlier models, suggesting the heliosphere is leakier than thought, allowing more cosmic rays to penetrate and potentially affect DNA mutation rates or cloud formation. For future exploration, the data informs designs for interstellar probes like Breakthrough Starshot, highlighting radiation hazards and magnetic navigation needs. As the Voyagers fade into silence, their echoes remind us of humanity's bold step into the unknown, transforming science fiction into cosmic fact. In conclusion, Voyagers 1 and 2 have not encountered alien worlds or dramatic anomalies, but have unveiled the subtle wonders of interstellar space: a humming plasma sea, intensified cosmic rays, draped magnetic fields, and a heated boundary wall. As of August 2025, with Voyager 1 at 15 billion miles and Voyager 2 at 13 billion, their detections continue to evolve our cosmic perspective, proving that even in the void, discovery endures. These pioneering sentinels, now silent witnesses to the galaxy, embody the spirit of exploration, their data a timeless bridge between our solar oasis and the infinite beyond.